Welcome back to Modern Operating System Design series on BitLearn. If you are new here, you may want to start with the earlier episodes where we look at how operating systems evolved and how different kernel structures shape everything that comes after that. So in this series, we are not learning what operating systems do. We are trying to understand why they are designed the way they are, what problems they were solving, and what trade-offs each design choice carries with it. So we will move from structure to execution to memory, eventually to how modern systems scale across different cores, machines, clouds, and each episode kind of builds on the previous one. So think of this as a slow, connected journey rather than a collection of isolated topics. So with that context in mind, let's continue. We are now looking at episode 3, which is going to cover processes and threads. So this is how the operating system creates the illusion of parallelism when you work with the operating system. So when we use a modern computer, it feels very alive with a lot of activity, right? You have music playing somewhere, you're downloading some files, you're compiling code. A dozen things appear to happen all at once. So this experience is so familiar that we rarely question how it happens. But underneath this kind of smooth surface or an act, there lies a very simple truth. If you take a CPU or a CPU core, it can execute only one instruction at any given point. Even on a multi-core system, each core follows the same rule. So parallelism, at least at the instruction level, is limited, and yet the system feels like it is doing a lot of things in parallel, and it feels like a very powerful system. It is, but it achieves that in a very different way. The operating system bridges this gap. It does this by using 3 foundational ideas. It uses processes, threads, and context switching. So together they create one of the most convincing illusions in computing. So let's start with processes. So this is where programs begin to come to life. So when you write your first program or when you have a complex program, it sits on the disk as a bunch of instructions that can be executed by the CPU. A process is what the program becomes when the operating system decides to run it. What do we mean by that? So when a process is created, the OS kind of reads all the program binary bits you have somewhere, it loads it into memory, and it creates an environment around that. It assigns memory, sets up registers, creates a stack, and gives the process an identity. So if you look at it from the inside, if you are the process experiences something very remarkable. No? It feels as though it owns the machine. The process is unaware of any other process running. So if you are the browser, you are not aware of any other application that's running. You don't know that there is a video editor that's trying to record something, or there is a clock which is trying to keep track of how much time was spent. You are not aware. You are just a browser, you are a process, and you are executing your instructions one by one on the CPU, and you feel like you own everything. So the process is kind of believes it has its own memory. It believes it has uninterrupted access to the CPU, and it also believes it is running alone. None of this is true, but all of it is intentionally made to feel true. It is designed to feel like that. So this is the power of process abstraction. By giving each program its own protected environment, the operating system enforces isolation. So one process cannot casually overwrite another's memory, or crash in one program does not automatically take the system down with it. So they exist not just for speed, but for safety and clarity. So they allow complex systems to be built from parts, and the components of a system can fail independently without affecting the entire end-to-end system. So now let's look at context switching. We understood what a process is. A process is a protected environment where your program and all its associated libraries and everything it needs to run is kind of encapsulated, along with a feeling or an illusion of being able to run these instructions independently on the CPU and having access to a lot of memory that it can use independently. Now let's look at context switching. So how does one CPU become many? How does it emulate so many things? So if a process feels like they are running continuously, yet only one instruction can execute at a time, it is because there are so many things happening behind the scenes. So if we take this example of a browser, and if I am the browser, I am the process, I believe I'm able to run my instructions one after the other on the CPU and get the desired result. But in reality, I'm interrupted hundreds or even thousands of times before I run my set of instructions. If I have 10 instructions, all 10 of them will not be executed in one sequence. What will happen is one of them is executed, then somebody, the operating system, will interrupt my process, keep it aside, give the entire processing environment to, let's say, the video editor, who believes that he has complete access. He will run his instruction. He's about to run his second instruction, again he's switched out. So that is context switching. So at regular intervals, the operating system interrupts the currently running process. It carefully saves the process's execution states, registers, counters, conditional flags, everything needed to resume execution later. Once this is saved, the OS restores the state of another process and hands control to that. So if I am the editor, if I am trying to capture video and do some things, I might be interrupted and the entire execution environment might be given to the clock. The clock is trying to keep track of how much time I consumed. So to the CPU, there is nothing more than loading and storing states. It doesn't care about which application you are running. To the process, execution appears seamless. So if I'm a browser, if I was trying to load a page, I know that my next instruction was to display this page. It happens seamlessly. I'm not even aware that I was interrupted. I was put to sleep. The clock took over and did something, and later the video editor took over and something, and then my entire context was restored, and I am asked to execute my next instruction. I'm not even aware of that. I, as the browser process, believe that I ran one instruction, then I simply executed the next instruction. That's not how it worked. But that's the illusion we give to the process. So if this switching happens quickly enough, let's say thousands of times per second, the user also perceives a very smooth multitasking environment rather than interruption. So to me, when I look at my machine, I can see the browser is running smoothly, the clock is ticking nicely, the video editor is fine. So time is sliced so finely that serial execution feels parallel. It feels like everything is running at the same time. Of course, this comes at a cost. Context switching consumes CPU cycles and it disrupts a lot of caches. We need to restore a lot. So that's why we need faster and faster CPUs to do this juggling across multiple processes. So operating system design is therefore not about eliminating limits, but about managing them invisibly. You can take the counter argument and try to build a system where you try to provide the entire CPU, the memory, everything to one process, let it finish its job, and then you can switch to the next one. But then you will quickly discover that it's not going to be really useful, because just because the clock is going to take some time to move its minute hand, I have to make all the other applications wait. The user is going to get pretty frustrated. Of course, we can talk of multiple CPUs handling each of these applications. That's where the cores come in. But there is something more interesting also. So let's look at threads. So this is concurrency within a process. I am a browser, but I have multiple tabs running. On one tab, I'm trying to load something, maybe ChatGPT or something. On another tab, I have something else running, maybe YouTube. So processes are powerful, but they're pretty heavy. Creating them one for each tab is going to take a lot of resources. Switching between them involves even significant overhead. So what we have is a concept called threads. To support this finer grained concurrency, operating systems introduce the concept of threads. So a thread is an execution path within a process. So it's like having these small context switches where everything else is left as it is, but it is still within the context of a process. I still have the same variables, I still have access to the same IO buffers. So multiple threads share the same memory and resources, but they get a chance to run their own independent instructions. So if we take the browser example again, and if I have 2 or 3 tabs running, just to simplify it, if we can assign one thread for each of these tabs, what will happen is my process is not yet switched out. I have a time slice of, let us say, for the sake of simplicity, 5 seconds to run my process, after which I will be switched out. Within the 5 seconds, I have a chance to run 3 different threads, 3 different tabs. So a thread is an execution path within a process. Multiple threads, they kind of share the same memory and resources. So this allows for different parts of the program to proceed independently. So it is like multitasking within multitasking. So one thread might wait for user input and release its execution. Another might perform a computation. A third one might be blocked on, let's say, user input or something. So because threads share memory and because they share memory, communication is going to be really fast. But the speed comes at a price. Shared memory means shared responsibility. So 2 or 3 tabs trying to access the same set of resources, they could be messing with each other. So this is where threads can interfere with each other in subtle but pretty dangerous ways. So we run into concepts of race conditions, deadlocks, inconsistent states, all of those things. So threads are therefore a trade-off between efficiency in exchange for complexity. So now that we know both the concepts, we arrive at a question. We need to choose boundaries. It is tempting to ask whether threads are better or processes, or vice versa. So this is the wrong question to ask. I'll tell you why. Processes and threads, they solve different problems. Processes draw strong boundaries, so they don't share anything between them. They isolate the failures, they kind of simplify your code, logic, everything. But threads kind of soften those boundaries to allow cooperation. So modern operating systems use both. Actually, we have threads available even at a CPU and a hardware level, which is where we have system threads and we have application threads. We have varieties of them. So the whole idea of choosing between processes and threads is not really a question, because processes are obviously meant for completely independent tasks where there is nothing that is overlapping between them. Threads allow us to run multiple independent execution pointers, but where there is shared data. So like I gave you a rough example, if you have a browser, the browser is the same, but you have multiple tabs, so they are execution. It's not really true. That's not how browsers are designed. Don't hold me for that. But the truth is, just to explain this better, if you know that you are building a browser has a set of resources available, you could treat that as a process, and each tab within that could be a thread, because they share the same IO. They have to render something, they have to accept input from the user, so they do the same task. So it becomes much easier to identify where processes can be used and where threads can be used. So now for a brief moment, let's look at user threads and kernel threads. So threads themselves can exist at different levels. In some systems, threads are managed entirely in the user space. They are simulated. The kernel sees only a single process, while a runtime library kind of schedules threads internally. So this allows for very fast thread creation and switching. However, if one user level thread blocks, for example, waiting for an IO, the entire process may stall, because all the other threads, they are not aware that they can pick up the CPU now. So kernel level threads, they kind of address this limitation by making threads visible to the operating system. The kernel schedules them individually, allows true execution, parallel execution, and prevents blocked ones from halting others. So to explain this, a user level thread is more like a finer grained multitasking ability at a user level, but it doesn't really map to a CPU thread or a kernel level thread. Whereas a kernel thread, once you assign it to a hardware level thread execution, lot of the thread management is managed by the CPU itself. So why don't we map every application thread to the kernel thread? Well, there are multiple reasons. So the kernel threads are, very raw in terms of having access to resources, whereas an application threads has some more protection. So there is some amount of protection that is added by application threads. And more importantly, we may not be able to map the number of user level threads to the kernel threads. Your CPU could support maybe 16 multi-threaded executions, whereas at an application level we may have 20. Why would we do that? Because there are many cases where the application can take a decision on when to pause a thread. The OS would not know that. The CPU would not know that. So if you are running, let's say, a 4-threaded CPU, a CPU that supports 4 threads, and you have all 4 of them blocked on IO, the CPU may not know that. It has to wait for its timeouts and then release one of the threads. Whereas at an application level, the operating system knows that I'm going to make a IO call, so I can actually make the call and pause the thread. I don't have to wait for the CPU to release it. So there are some pros and cons in using application level threads and kernel level threads. We can talk about that in detail a little later. So this kind of added overhead, it enables some scalability and fairness in terms of scheduling. Now let's look at the slightly deeper idea. At no point does the operating system violate the laws of hardware. What do I mean by that is, processes create the illusion of ownership, threads create the illusion of simultaneous execution. These are not tricks, they are disciplined abstractions. And we weave it all together to give the illusion that a lot of these things are happening in parallel on my machine, or at the same time I see a video window, I see my webcam streaming something, there's something else. So it's all a grand illusion, but it works beautifully. So the true achievement of an operating system is not raw speed, but it's the ability to make limited hardware feel like it is very rich, responsive, forgiving, and not waste any hardware resources waiting for somebody to finish his job. So far we have explored how the operating system creates this illusion of parallelism. In the next episode, we will confront a slightly harder question. When many processes and threads want the CPU at the same time, who decides who runs and when? So that question takes us into CPU scheduling, policy, fairness, performance, all of those things. So I hope you're enjoying listening to this summary of how the operating system works. Please make sure you like and subscribe this video if you're enjoying this. Drop some comments if you want me to change something, like how I convey some of my ideas. Meanwhile, keep learning, and I'll meet you in the next episode. Thanks for watching.